Welcome to our next video. We're going to see a small example on eigenvectors and eigenvalues here. So let me first write down the example. We are given the following matrix: A equals 5/2 minus 1 minus 1/4 and 5/2. Now you will hopefully recognize that matrix. This is precisely the matrix that we got for our little example of a system of differential equations, the raccoons and squirrels example. You already know that there is a transformation to a diagonal form. So let's see if we can actually get the right results here using the methods that we discussed. We want to determine the eigenvalues and the eigenvectors and see if we can get a transformation to a basis of eigenvectors of R2. So the first step in that is to determine the characteristic polynomial. We do that by computing the determinant of A minus lambda E2. So the determinant of, well, let's see, A is 5/2 minus 1/4 minus 1, 5/2. And we subtract lambda on the diagonal here. So the determinant of this is 5/2 minus lambda squared minus 1/4. Let's reformulate that just a little. So we'll leave the first factor as it is. We'll write the second factor as 1/2 squared. And then you'll hopefully recognize this as a binomial formula. So this here is the first factor, a squared minus, this is b squared. And as you know, this is a plus b times a minus b. So what we get here is 5/2 minus lambda plus 1/2 times 5/2 minus lambda minus 1/2. And after the simplification, 5/2 plus 1/2 is 6/2, so we get 3 minus lambda. And 5/2 minus 1/2 is 4/2, so we get 2 minus lambda here. And that means the eigenvalues of A are lambda 1, let's take the smaller one first, that is 2, and lambda 2, that is 3. So these are the two eigenvalues. Next, we need to compute the eigenvectors from that information. So part 2. Eigenvectors. We have to do that separately for the two lambdas. So let's start with lambda 1 equals 2. For this, we consider the matrix A minus 2 E2, or so I can write down A first, 5/2 minus 1 minus 1/4 and 5/2, and then we subtract the eigenvalue on the diagonal, so minus 2 in both of these entries. What we get here is then 1/2 minus 1 minus 1/4 and 1/2. To determine the kernel of that, we basically have to use Gaussian elimination to solve the equation system. So what we do here is we add 1/2 times the first row to the second one. And that will give us 1/2 minus 1 here, and 0, 0 in the second row. So that means the eigenspace of the eigenvalue 2 for the matrix A is the span of 2, 1. Okay, so 2, 1 is an eigenvector. Of A for eigenvalue 2. And by the way, so is every scaled version of that vector, of course. Yeah, so 4, 2 would also be a valid answer, or 1, 1/2, or -2, -1. Every multiple is a valid eigenvector. And you can choose whatever you want. The result for the diagonalization will always be the same. Let's do the same for lambda 2. That is 3. Again, we compute A minus 3 E2. Same idea. We have the matrix A, 5/2, minus 1/4, minus 1, 5/2. And this time we subtract 3. And that gives us minus 1/2, minus 1, minus 1/4, and minus 1/2. So this time, to do the Gaussian elimination, we subtract 1/2 of the first row from the second one. And we get, first row stays the same, minus 1/2, minus 1. And now the second row again becomes 0, 0. And that means the kernel of that matrix A minus 3 times E2. That's the eigenspace that we are looking for. The kernel is then spanned by the vector -2, 1, for example. And again, each multiple of a vector will do. Okay, so we have two eigenvectors. One is 2, 1, the other is -2, 1. Those are linearly independent. So we do in fact have a basis of R2 that consists of eigenvectors of A. So third part is the question, is there an eigenvector basis? And in this case, the answer is yes. 2, 1, -2, 1 is a basis of R2. That consists of eigenvectors of A. So in this case, there is indeed such a basis. And now finally, if we wish to compute the transformation, that is easy to do. Basically what we do is we take the eigenvectors, we use them as columns of the transformation matrix. So we have 2, 1 here, -2, 1. That is our transformation matrix S. And if we do that, then S to the -1 AS will be the matrix 2, 0, 0, 3. One thing I'd like to mention is the order of the eigenvectors and the order of the eigenvalues in the diagonal matrix. Those two correspond. So in this case, we took this eigenvector here. That belongs to the eigenvalue 2. So there's a 2 here. And we took this eigenvector here that corresponds to the eigenvalue 3. And there's a 3 here. So these correspond. And of course, ordering the columns of A as we did was a very deliberate choice. So we could also have taken, let's call that T, the matrix where we just use the columns in the other order. So -2, 1 first, then 2, 1. If we take this as a transformation matrix, it works as well. But in that case, we also reverse the order of the eigenvalues on the diagonal matrix, right? So in that case, what we get is, again, -2, 1 here corresponds to the 3. And now, as -2, 1 is in the first column, the 3 is also in the first column. And same thing for that other one here for the 2. Okay, that concludes this little example here. That shows you how I actually got the transformation matrix that I've shown you earlier already. And the next question that we're going to tackle is, what can we do if the characteristic polynomial does not have real roots? And I already said in that case we'll have to resort to complex numbers, so we're going to talk about complex numbers in the next video.